can see my screen now, my presentation. Okay. So my presentation is about the pelvic mechanisms of gait rehabilitation systems. I will try and summarize the importance of pelvic actuation and the types of pelvic mechanisms that were built and studied publicly until August 2020. Saunders et al. Had a theory back in 1953 that stated that mechanisms at knee, foot, and hip level, together with pelvic movements, are responsible for reducing the vertical movement of the center of mass. The center of mass vertical remains inside the base of support, balance is acquired, the risk of fall is prevented, and natural gait patterns are achieved. This theory came to be known as the 6 determinants of gait theory. These determinants are mechanisms that aid the knee in the stance phase, mechanisms for knee action, foot mechanisms, pelvic transverse rotation, pelvic tilt, and lateral displacement of the pelvis. 3 out of the 6 determinants are pelvic motions, which highlight the importance of pelvic control during gait rehabilitation. During walking, there are 6 pelvic movements described in all 3 planes, 3 translations, mediolateral, anteroposterior, and superior-inferior, and 3 rotations or angular displacement. Tilt or anteroposterior rotation is about the transverse axis. Obliquity or up-down rotation is about the sagittal axis, and transverse rotation or internal-external rotation is about the vertical axis. The pelvis mechanism is a component of gait rehabilitation systems that currently is underdeveloped. In order to achieve natural pelvis movements, it is necessary to develop multi-degree of freedom pelvis mechanisms that provide assistive force field to the pelvis and control all 6 degrees of freedom of the pelvis. Otherwise, pelvis mobility constraints and human-robot joint misalignment occur during gait training, leading to improper execution of balance responses and increasing the risk of fall. In order to assess the different approaches that have been proposed to address these needs, a review of the current pelvis mechanisms was needed. The aim of this review was to help researchers identify weaknesses and come up with solutions for new generations of gait rehabilitation devices in what concerns the pelvic mechanism. The data on current gait systems with pelvic mechanisms was collected on the 26th of August 2020 from the following databases: PubMed, IEEE Explorer, ResearchGate, and Web of Science. The selection criteria included all devices with at least 1 actuated pelvic degree of freedom and excluded the systems with all pelvic degrees of freedom, either passive or restricted, as well as those with pelvic support only for registering data and not for controlling pelvic motion. 16 devices that met the criteria were identified. If a system had more versions or prototypes, the latest one to meet the criteria was chosen. This is the list and overview of the systems. I will talk about the most important aspects in the next slides. So, as shown in the table, overground systems and exoskeletons are the most common types of systems that can offer a pelvic mechanism. Overground systems use the flat surface of the environment to train patients, which can lead to a couple of the advantages. They are suitable for training of turning maneuvers, a development that is highly necessary to avoid obstacles. Also, all fall experiments can be performed or exercises on unstable grounds that teach balance. Applying unexpected perturbations help study the motor responses of the central nervous system in order to restore balance and prevent fall. All of these trainings and experiments require good control of pelvis motion and of the center of mass. Nature Gates 2, which stands for Natural and Tunable Rehabilitation Gait System, Walk Trainer Gero 2, which stands for JACE Active Robotic Walker, and Assist on Gait are overground systems. They use a mobile base or platform for walking on flat surfaces. With the exoskeleton systems, natural gait patterns can be achieved by using a high number of actuated degrees of freedom. This, however, requires many mechanical parts, which raises the complexity of the mechanism and thus the cost and weight of the system. The heavier the exoskeleton is, the more discomfort the patient feels and the more abnormal the gait patterns become. This vicious cycle results in unsuccessful recovery if solutions are not found. Lopez 2, Locomat Pro, Alex 3, which stands for active leg exoskeletons, RGR Trainer, which stands for robotic gait rehabilitation trainer, COAC and lower limb rehabilitation robot are treadmill-based exoskeletons that actuate pelvis movements. Lopez 2 has come up with a solution in respect to the weight problem of the exoskeletons. The mechanical part and the actuators are located in a unit behind the patient called shadow leg. And the patient is connected to this unit with clamps. This way, the patient does not bear the weight of the exoskeleton. Locomat Pro, Alex 3, COAC, and lower limb rehabilitation robot, on the other hand, support the entire weight of the exoskeleton with the help of mechanical arms attached to the fixed unit located behind the patient. RGR Trainer actuation system is gravity compensated as well. Treadmill-based exoskeletons usually restrict pelvic motions. This can lead to less satisfactory functional outcomes. Such exoskeletons are Locomat Pro, Alex 3, and COAC. Other treadmill-based systems with pelvis mechanisms are pelvic manipulators, such as PAM, which stands for Pelvic Assist Manipulator, IBWS, which stands for Ischiatic Body Weight Support System, and Gait Rehabilitation Robot. And cable-driven robots, or Y robots, stand trainer, which can also work with force plates and stringman. There are two bodyweight support concepts in the literature: the cable harness bodyweight support concept, when the user wears a harness system, and the structural bodyweight support concept, when the user's body weight is held by a robotic mechanism at waist or back level. Cable harness bodyweight support systems are attached to the suspension mechanism, usually through one single point. This results in lack of control over the direction of the harness when the user tries to walk. However, this can be compensated by the use of a pelvic frame. The most common pelvic robot-human interface is a pelvic harness, brace, or belt, which is in contact with the end effectors that provide active movement of the pelvis. For cable and wire-driven robots, the interface is represented by either a harness or pelvic and trunk belts on which the cables are attached. The IBWS has a pelvic socket. In order to firmly fit and attach the user's particular anatomy, it is designed with 6 adjustment degrees. Although it allows stable body posture with free movement of arms and legs, its structure is rigid and might create discomfort when walking. Another notable aspect is that there is no perfect harness. All of them induce focal pressure and restrict functional normal gait movements. A number of 6 systems do not allow all 6 movements of the user's pelvis. Locomat Pro and Gait Rehabilitation Robot allow only 3 motions: mediolateral translation, vertical translation, and transverse rotation. The rest of them being restricted. COAC has tilt and obliquity restricted, while Alex 3 and Assist on Gait have only 1 restricted motion: tilt for Alex 3 and obliquity for Assist on Gait. 4 systems, Locomat Pro, Alex 3, COAC, and Gait Rehabilitation Robot, have the most important pelvic motions restricted: lateral translation, transverse rotation, and tilt, which are the 3 determinants of gait related to pelvis motion. Only Nature Gaits 2, Stand Trainer, and Walk Trainer provide actuation for all 6 movements of the pelvis. Lopez 2, PAM, RGR Trainer 02, IBWS, Stringman, and TPMAD, which stands for Trunk and Pelvis Motion Assistant Device, actuates some motions, while the rest of them are passive or free. RGR Trainer and TPMAD provide only 1 active movement, the rest of them being free. Lopez 2 and Locomat Pro provide only 2 active movements. The trajectory of the center of mass is strongly influenced by the restricted motions and also by the free movements of the pelvis if the user has gait dysfunctions. Therefore, theoretically, only Nature Gaits 2, Stand Trainer, and Walk Trainer are capable of providing the most natural center of mass trajectory. However, Nature Gaits 2 is known to affect the ground reaction forces, and therefore it might influence the center of mass trajectory as well. Lopez 2, PAM, 02, COAC, and low limb rehabilitation robot partially provide the control of center of mass by reducing the trajectory excursions in some axes, but not not all. Traditionally, the interface between an actuator and its load was stiff. The advantages for reducing the interface stiffness are lower reflected inertia, greater shock tolerance, more stable and accurate force control, and the capacity for storing energy. A series elastic actuator has an elastic component, a spring, that is able to support loads and is not too stiff. These compliant actuators are designed to reduce the net human joint torque using the spring during specific gait subphases. There are two important terms. The first is quasi-stiffness, which represents the relation between torque and joint angles and does not reflect the actual stiffness of the biological joints. The other term is human joint stiffness, which represents the association of muscle activation, velocity of its contraction, and the elasticity of muscle fibers and tendons. The actuators should reproduce both quasi-stiffness and joint stiffness. Later is more difficult to obtain due to the complex modulation of muscle and joint level, while quasi-stiffness can be easily measured. Compliant actuator technology is still in its early development. How compliance is modulated and how it influences global stability, it is not yet clear. The answers would help to develop effective systems for gait rehabilitation by reproducing typical gait patterns and corresponding round reaction forces. Walk trainer and strongman have 6 actuated degrees of freedom for pelvis movements, while stand trainer is customizable and can provide up to 6 active degrees of freedom. PAM, Nature Gates 2, IBWS, and Assist on Gait have a total of 5 actuated degrees of freedom. RGR trainer and TPMAD have only 1 actuated degree of freedom, and lower limb rehabilitation system provides only 2 active degrees of freedom. Walk trainer has selective compliance, which means that a physician can decide what degrees of freedom should be made compliant. In the early stages of rehabilitation, the patient is unable to move a part of all of the lower limb segments. Therefore, the system should be able to make the movements for the patient. However, after a period of time, the patient might start recovering motor control, and the system must be able to adapt and actively assist the patient. This means the patient should start the movement and the system should adjust the trajectory and control the range of motion. Back drivability is used to control the force applied by the system on its user, without using force sensors and implementing a feedback loop. Perfect back drivability is when the torque is 0 with no friction or stiffness involved, which is difficult to achieve if not impossible. This is why systems that provide high mechanical transparency have high back drivable actuators, meaning that the mechanical transmission friction and the torques are as close to 0 as possible. This allows the robot to follow the user, which moves freely, unconstrained. A number of force systems are not back drivable: Nature Gates 2, Walk Trainer, IBWS, and TPMAD. And 5 systems, Stand Trainer, 02, Assist on Gait, Stringman, and TPMAD, do not provide the operating mode in which the robot is in control and the user follows the robot passively. There are 8 systems which are capable of following the patient and intervening throughout the entire training session, even if not needed. Stand Trainer, Locomat Pro, Alex 3, 02, Co-Walk, Assist on Gait, Stringman, and TPMAD. And the only one system, Locomat Pro, has an operating mode in which the robot intervenes only if needed when the patient leg's trajectory passes outside a certain virtual field. Conclusions. The main objective of the gait rehabilitation systems is to help patients achieve the highest possible level of functional independence given their situation. Future research directions for system improvements should consider motion intention recognition systems based on brain-computer interface, functional electrical stimulation, EEG, or other technologies that can be applied in a closed biofeedback loop in order to predict and assist the patient's movements and adjust their trajectory and range of motions only if needed. It would make a huge difference if it can be implemented for assisting the pelvis as well as the impaired lower limb. Other challenges address the back drivability and the control system that could be able to compensate the device's inertial effects and therefore synchronize automatically the device's motion with the user's motion. Regarding the harness, although there is no perfect harness, it can be equipped with pressure sensors to establish the degree of pressure and help the patient relieve it by making adjustments. Future research is needed to conclude whether treadmill kinematics are different from overground kinematics, and future objectives should include the increase of the addressability of these gait rehabilitation systems in order to cover more complex gait disabilities generated by diverse pathologies. This can be achieved by giving up the mobile base of overground systems and coming up with a better mechanical solution that can enable the patient to train in more complex environments, such as different ground textures and stairs. Thank you.